Good morning, everyone. My name is Songwei Zhou. I'm a research scientist at Johns Hopkins University. It's a great pleasure to present our work today, analyzing pancreatic tumor by synthesis. This is a joint project at Hopkins between the CS department and Johns Hopkins Medicine. It's called Felix. The name was taken from Harry Potter, a liquid luck that makes the drinker incredibly lucky for a period of time. Here in the Felix project, our goal is to use AI algorithm to detect the pancreatic tumor as early as possible. It has been funded by the Lost Garden Foundation since 2017. Radiologists can detect the pancreatic cancer from CT images, but early cues are very subtle and easy to miss unless the pancreatic cancer is already suspected. This motivates us to develop the AI algorithm for detecting and localizing pancreatic tumors. We particularly interested in detecting small tumors that are potentially treatable. This talk will concentrate on work done by the CS team. The Felix project has been very successful. Our AI algorithm can already achieve 97 and 99 sensitivity and specificity for pancreatic tumor detection. We only consider a tumor detection to be successful if the AI can also localize it. That means a detection in the wrong part of the pancreas will be treated as a failure. Performance seems comparable to expert radiologists, but it's hard to do a fair test to evaluate it. So I put a question mark here. It is because the radiologist usually can search for the pancreas tumor not just based on CT images, but also use extra information such as the patient symptom, medical history. Another point I want to make is that most literature only report radiologist performance in detecting pancreatic tumor at relatively late stage, which can be pretty high. In addition, we also evaluate the generalizability of our AI models across multiple hospitals in the US and Germany without training on this outside dataset. The performance degrade a little bit, but both sensitivity and specificity are still above 90. This great performance comes with great cost, however, because it requires an annotated dataset to train and test the AI algorithm. This number can be very, very big. In the Felix project, we collect and annotate over 3.8 million CT images. That is over 5,000 patients. There's a need for even bigger datasets from multiple hospitals to fully evaluate the reliability of AI. As you can see, even the institute with enormous resources like JHU, annotating cancer image is still a big headache, not to mention the public available datasets such as MSD pancreas, which only provide hundreds of annotated CT for both training and testing. Lack of annotated data is a big issue to really solve the detection of pancreatic tumor. Annotating tumor images is hard. Tumors are very small compared with most objects annotated in 2D natural images. Tumors only account for 0.0001 in a three-dimensional CT image. For human annotator, detecting the tumors and providing per-voxel contour of each tumor are time-consuming and require specialized medical knowledge. On the left is the raw CT image, and on the right is the annotated image. At Hopkins, for over 5,000 CT images, we not only annotate the pancreas, but also annotate the tumors of 3 subtypes: cyst, PDAC, and PNET. In addition, we also annotate pancreatic duct because a dilated duct can be a great indicator of tumors. Annotating all these structures can take a radiologist 15 years to complete. And we spend several radiologists and multiple medical trainees to complete this big data set. And that's the story behind the success of Felix project. Is there any way to reduce the annotation cost? From last year, we start to explore a new direction, and that is the main topic I'd like to share with you today. We looked into synthetic data. We have created artificial tumors to help AI detect early-stage cancer and show that AI trained only on synthetic tumors work as well as AI trained on real tumors. That means even if you don't join JHU and you do not have access to our Felix dataset of 5,000 annotated CT images, there's a possibility that you can use publicly available data to achieve performance as high as our algorithm. Synthetic data have so many advantages. They are cheap, fully generated by algorithm, and they are perfectly annotated. They have no privacy issue because it's not based on specific patients. We can generate as many as we want to train the AI. There are many other advantages to use synthetic data as validation. Test set of real tumors, especially early tumors, is always very small. It is hard to find which AI is good at and which is bad at. We can manipulate synthetic data to more efficiently find the AI's weakness. But this is relatively advanced topic and require longer discussion. For this talk, my biggest wish is to convince you that synthetic data can be useful for training AI. Let's start from very beginning. How good is current synthetic data? Recent years, generative AI prompted by text or latent variables can now generate diverse and realistic images with some compositionality. For example, an astronaut riding a horse. This is a thing never happened in the real life, but can be pretty realistic when generated by the most advanced generative AI. But their capability in generating medical images are poor. These are two examples generated by GPT-4o. The prompt was to generate 2D CT images with liver and pancreatic tumors. Neither the tumors or CT images themselves are realistic enough. This is understandable because these generative AI may not be trained on sufficiently big number of medical image data. Early this year, NVIDIA released a generator specifically designed for medical image data, which can generate a pretty realistic anatomical structure. But this tool, called MICCAI, still have issue generating good enough tumor example. Our team at Hopkins has been focused on generating realistic tumors since last year, and we have made great progress on this. With our progressive investigations, the generative tumors become more and more realistic as shown on the right. In our recent work, we surprisingly showed that training AI only on synthetic tumors yield very high performance level. It is comparable to AI trained on large number of per voxel annotated tumors, and particularly helpful for detecting tumors at very early stage. Our observation is that early-stage tumors often have a similar appearance in the CT image, whether they come from the liver, pancreas, or kidney. This is because the tumor usually starts from a small dark dot in the image and then grow up to have arbitrary shapes and a complex texture. At the very beginning, they are almost spherical and with a simple texture that is similar to Gaussian noise. Collecting scans with early-stage tumor is such a painful, hard task, but luckily, generating early-stage tumor is relatively easy. So we move forward to turn this observation into an actionable tumor synthesis method. We use a diffusion model to overfit the simple shape and texture of early-stage tumor. For example, we train a diffusion model to generate liver tumors. When you heard the diffusion model, you might start worry about the number of annotated data needed to train this model because they are well known to be data hungry. In computer vision, training diffusion models to generate a cat and a dog require enormous training data. This is because these are complicated objects. But for early-stage tumor, whose shape is almost spherical, whose texture is similar to noise, we found that only one or two examples of early-stage tumor are sufficient to train diffusion model. In another word, it's sufficient to overfit the diffusion model. After training diffusion models with a few early-stage tumor examples in the liver, it is ready to generate many tumors on top of other healthy livers and on top of other organs such as pancreas and kidney. Because as you can see, the early-stage tumor in these organs are so similar to each other, and the only variance is the surrounding of the tumors instead of the tumors themselves. To quantify our hypothesis that early tumors from different organs appear similarly in CT images, we mix the generative tumors across organs and perform a reader study that asks radiologists, where do you think the generated small tumors originally come from? The liver, pancreas, or kidney? In our study, 3 radiologists' answers are equal to random guess, meaning that they cannot tell where the tumor originally comes from. We also train a 3-way classifier on these tumor images, and the classifier's answer on the test set also equal to random guess. This study result suggests that early-stage tumors are visually similar across the liver, pancreas, and kidney due to their spherical shape and simple texture. We also compare radiomics feature on these early-stage tumor examples and did a TSNE analysis on these features. We learned from the plot that the shape and the texture-based radiomics feature cannot really tell which organs our early-stage tumor come from. They are all spread in the entire space. In addition, we consult these results with radiologists and make description of early-stage tumor in different organs. This description basically tells us that tumors at very early stage appear similarly across different organs. They have a roundy shape and a hypo-enhancing texture. This observation makes everything so easy to do. First, we do not need many data to train the diffusion model. Second, these generated tumor can be added to different organs. Then we did another human study on the realism of tumor synthesis. Essentially, we ask human experts if they can tell the tumors in the CT images are real or generated by our algorithm. Our synthetic tumors are realistic that even senior radiologists can only achieve around 70% accuracy on this task. And the junior radiologist can achieve accuracy worse than random guess. Here are 8 examples in this test. If the screen quality allowed, would you be able to tell which one is real and which one is a synthetic tumor? It's a tricky question because all the examples are generated by AI algorithm. Next, I want to present the result of AI trained on this synthetic tumor performed on detecting real tumor in the CT image. I use a liver tumor as an example. As you can see on the right, AI trained on the synthetic tumor with no annotation effort can achieve DICE score of around 60. And AI trained on real tumors with per voxel annotation can achieve DICE score of 58. And their performance is pretty similar when evaluating on the real test set. We present 3 different methods including handcraft method or learning-based method to generate synthetic tumors in this publication. The conclusions are similar that even we trained AI on fake data, it worked very well on detecting real tumors in CT images. And especially when training AI on both real tumor and synthetic tumor, the performance was significantly improved. This has been evaluated on tumors in the liver, pancreas, and kidney. More importantly, since collecting small tumors in real CT scan is extremely difficult, AI often performs poorly on detecting small tumor due to the lack of sufficient training examples. With the help of synthetic tumors, practically, we can generate as many small tumors as we want on healthy scan. When training on a large number of synthetic small tumors, we show an improvement of 10% sensitivity in detecting tumors less than 5 mm in the liver. Note that in all the studies, we use the real tumor for evaluation. So this technique is needed for early tumor detection because early sign of cancer can be subtle. According to the literature, half of the liver cancer are missed by radiologists. It is also needed for AI development because a CT scan with early cancer are limited and the annotation for these cancer are hard. We create a large multi-institutional synthetic tumor dataset with per voxel annotation. This includes tumors in the liver, pancreas, and kidney. We call this dataset Abdomen Atlas X. It includes over 9,000 CT images and 66 tumor masks. This dataset can be very useful to train AI. It is much bigger than existing public tumor datasets, which are often with the hundreds of annotated CT scans. Then I'd like to present two topics that synthetic tumors can be very helpful. First, AI generalizability. Many literature, including our own results in the Felix project, shows that AI performance can be downgraded when evaluated on images that are very different from the training set. For example, AI can perform very well when evaluated on CT scans of similar population and created by similar CT scanner as training set, while it has significant job when evaluated on CT scans of different population and scanners. This problem can be much bigger if the AI was trained on a limited number of data with some bias. This often happens in the tumor-related task because public available dataset for this task is really too small. But collecting CT scans without annotation from target hospital is relatively easy, and perhaps we can collect many patients of same demographic. It is okay if these CT scans are without tumors or without per voxel annotation of the tumor, because we can always introduce the synthetic tumors to these scans and use them to train AI model. As expected, we found that training AI on a few real data with per voxel annotation, supplemented by many scans from target hospital with synthetic tumors and synthetic annotation, perform very well in these new outside hospitals. This is an effective and cheap way to quickly make your AI work on many different hospitals. The second topic that I think synthetic tumors can be impactful is efficient manual annotation for more tumor data from different hospitals. Again, public available tumor-related datasets are way too small. Our dataset of 9,000 synthetic tumor CT scans can be very useful to train a strong AI and help annotate many more real tumor CT scans. We adjust the AI prediction threshold to make the AI overly sensitive, meaning that the AI will almost not miss any tumors in the image, but it will inevitably introduce many false positives. In this specific scenario, handling false positives is much easier than handling false negatives. Our strategy is to use the radiology report to tell us whether this CT scan contains tumors. Radiology reports are usually available in the clinical data repository. For CT scans without tumor, we can automatically remove all the false positive prediction without any human intervention. For CT scans with tumors, after adjusting AI threshold, we will have a very high sensitivity of tumors with per voxel AI prediction already, and have several false positives per scan. This requires human effort to remove false positives. In our study, we found that AI can achieve 99% sensitivity with only 0.6 false positives per scan for pancreatic tumor detection. That means radiologists only have to remove one false positive in every 2 CT scans. This strategy is much easier than providing per voxel annotation for the tumors from scratch. We did a reader study to estimate the time. To create per voxel annotation, it will cost the radiologist 4 to 5 minutes to annotate a tumor. And to remove the false positive, it only costs them less than 5 seconds. So now we are working on using this more efficient annotation strategy to annotate real tumor in much bigger database, and it will expected to release next year. To summarize, I present several recent studies on synthetic tumors. We show that they are very promising as additional training data. Given the very limited number of public available tumor dataset, we provide 9,000 synthetic tumor CT scans for the community to make the AI stronger, more generalizable to different hospitals, and provide an efficient way to annotate more real tumor CT scans. Thank you very much for your time. If you have any questions, please feel free to email me.